Hi everyone, my name is Apuraj Garakapati. Welcome to my YouTube channel Amazing Apai. Knowing what the IOCDS is gives us a name. Knowing why it exists gives us the real story. Imagine walking into a huge control room where many operating systems are running at the same time on the same Enterprise Z machine. Each one needs storage, network paths, and devices, but they cannot all grab whatever they want. If they did, the environment would become like a crowded city with no traffic lights, no lanes, and no rules. This topic explains why the machine needs one trusted IO map before any operating system starts. Once that idea is clear, the rest of IO architecture becomes much easier to understand. A normal small server is easy to imagine. One operating system owns the machine, and most hardware belongs to that one operating system. A large Z environment is different. It can host many logical partitions, and each partition may behave like a separate computer with its own operating system. Now the challenge becomes more serious. Who is allowed to reach which storage? Who can use which path? Which resources are shared, and which must stay private? The IOCDS exists because this environment is too important and too large to depend on guessing or automatic discovery. Scale is the first reason the IOCDS exists. Think about a building with many apartments but only a limited number of roads, elevators, and entrances. If every resident tries to use everything without rules, the building quickly becomes chaotic. A Z system has the same basic challenge, but with operating systems instead of residents. Many LPAR can run side by side, and each one needs access to storage and network resources. The physical ports are real shared assets. The IOCDS gives the machine a controlled plan, so every LPAR gets only the IO paths it is supposed to use. It is tempting to compare this environment with a smaller computer where a device is connected and the operating system discovers it. That simple idea does not scale safely when many operating systems are sharing one enterprise machine. Imagine a hotel where every guest key opens every room because the building decided to discover doors automatically. That might sound convenient for a moment, but it would be a security disaster. In the same way, the machine cannot allow every operating system to discover and use every attached resource. Access must be described before startup and enforced by the hardware. Before we move ahead, please take a second to like on this video. A like tells me that you enjoyed this topic. Your support helps Amazing Apai grow naturally. The IOCDS is the solution to this scale problem. Think of it like the master map used before opening a huge airport for the day. Before flights begin, gates, routes, access areas, and restrictions must be known. In the same way, the IOCDS is loaded before operating systems start using resources. It defines which partitions exist, which paths are available, which devices can be reached, and which access boundaries must be respected. Without this central map, the shared environment would be exposed to collisions, confusion, and accidental access. Timing matters. The IOCDS is not a casual setting that appears after the operating systems are already running. It is loaded during the machine startup process, before the operating systems begin normal work. This is like setting up the traffic lights, lane signs, and road closures before rush hour starts. If the rules are in place early, every driver enters a controlled environment. In the same way, when each operating system starts, the machine already knows which IO paths are allowed and which are not allowed. The IOCDS is powerful because it is not just a suggestion written in a document. Once loaded, the machine enforces the definitions. Imagine an office building where an employee badge opens only the floors that person is allowed to enter. The employee cannot simply decide to visit a restricted floor. The access system stops them. In the same way, if a partition is not defined to use a path or device, the operating system inside that partition cannot simply take it. This is what makes shared infrastructure safe for serious workloads. One practical reason the IOCDS exists is to support separation of workloads. Picture a company running production work and testing work on the same large machine. Production data must stay protected. Test activity must not accidentally touch production storage. The IOCDS acts like a formal contract between the workloads. It says which paths production can use, which paths test can use, and which resources must remain separate. This gives the organization the benefit of shared physical power without losing the safety of isolation. The apartment building story is a simple way to remember the need for IOCDS. A building may have many apartments, but residents cannot open every door, use every private storage room, or control every utility area. The building works because each resident has access to the right spaces and is blocked from the wrong ones. A large Z system follows the same idea. Many LPAR may live on the same physical machine, but each needs carefully controlled access to IO resources. The IOCDS is the access plan that keeps the shared environment orderly and safe. Before we move ahead, please take a second to share on this video. Sharing helps this video reach friends who may also enjoy anime, gaming, travel, cricket, chess, career basics, or personal stories. Your support helps Amazing UP grow naturally. Some workloads are more sensitive than others. For example, a critical production workload might require dedicated channel paths that no other partition can use. The IOCDS allows that kind of design because access is explicit. It is like giving an emergency service a private road, so it is not delayed by normal traffic. Other workloads may share general paths, but the sensitive workload receives protected routes. This is one reason the architecture is so valuable in environments where reliability, separation, and control matter. The IOCDS does not solve the access problem with one simple switch. It defines the environment at several levels. First, it helps describe the logical partitions. Then it describes channel paths. Then it describes control units and devices. It can also define specialized functions. This is like planning a secure campus. You do not only decide who can enter the campus, you also decide which building, which floor, which room, and which equipment someone can use. The layered model makes the environment flexible without becoming uncontrolled. Without a central AO map, the environment would become risky very quickly. Imagine a city where every driver chooses any lane, ignores traffic lights, and parks anywhere. The problem is not that people are trying to cause damage. The problem is that there is no shared structure to prevent mistakes. In a large Z environment, uncontrolled I/O access could lead to collisions, accidental data exposure, and unclear ownership of resources. The IOCDS turns that dangerous uncertainty into deliberate design. The IOCDS design has historical roots in early mainframe architecture. Some details may feel old at first, but the underlying problem is still very modern. How do you allow many workloads to share powerful hardware while keeping them isolated and predictable? The answer was to separate the logical definition from the physical hardware and use a central configuration that the machine can enforce. That idea has lasted because shared computing still needs the same kind of discipline today. Some IOCDS rules feel old because they come from an era when computing used fixed formats and punched cards. That history explains why columns and statement order matters so much. But the older style should not distract from the purpose. The configuration must be read precisely. A map with vague directions is dangerous when the environment is large and important. The strict syntax forces the map to be explicit, predictable, and consistent. Before we move ahead, please take a second to like on this video. A like tells me that you enjoyed this topic. Your support helps Amazing UP grow naturally. Many people now talk about virtualization, shared platforms, and isolated workloads as if they are new ideas. In this architecture, those ideas were part of the foundation much earlier. The IOCDS supports a world where many logical environments can run on one physical machine while still staying controlled. This is why the IOCDS should not be viewed as an extra file someone added later. It is a core part of how the platform makes shared computing safe. The easiest way to remember this topic is to connect three words: define, separate, and enforce. First, the IOCDS defines the machine's IO world. Second, it separates workloads, so one partition does not accidentally use another partition's resources. Third, the hardware enforces those definitions. This is why the IOCDS exists. A shared enterprise machine can be powerful only when the sharing is controlled. Without the IOCDS, sharing would become uncertainty. With the IOCDS, sharing becomes architecture. The main takeaway is that the IOCDS exists because scale and isolation must be handled before work begins. Many LPAR may share one physical machine, but each one needs controlled access to IO resources. The IOCDS provides the central definition, and the machine enforces it. This is what allows production, test, and sensitive workloads to live on the same powerful platform without losing separation. Once you see it this way, the IOCDS stops feeling like just a configuration file and starts looking like the rulebook for safe shared computing. This topic answered the why. The IOCDS exists because a large shared machine needs a trusted I/O map before operating systems begin using resources. The next topic naturally asks how that map becomes active. That brings us to initial machine load, the startup event where the machine reads the IOCDS and uses it to build the active I/O environment. Keep this story simple. First, we need rules. Then we need to load those rules. Then operating systems can begin working inside the boundaries those rules create. If you enjoyed this video, please hit the like button and subscribe to Amazing API. Subscribing makes sure you do not miss the next video, and it gives me motivation to keep improving the quality of every upload. Thank you for being here, and I will see you in the next one.